Recording's rolling. It is Thursday, September 4th. So we're on lesson 1-3 today. So going over this last class, this ends up being a shorter section than each last 2 days. Each last 2 days will take most of the class to go over, but yeah, this one only takes about half the class. Then you'll have about the last half class day to find these puzzles, get them ready day, get you guys assignment. One is little slip of paper, might possibly do within reach today. And so these are due on Monday the 8th. So got a few from lesson 1, lesson 2, and lesson 3, which I'm about to cover today. There's only a few here because, okay, probably that's all. It's really worth finding. So you can knock out these puzzles today and also tomorrow. Tomorrow I had allocated as a puzzle and Alex day anyway, so I'll just see that tomorrow. Tomorrow's a short day anyway. And then, guys, eventually be looking for a quiz on module 1, looking at next Friday. So I still have to cover modules or lessons 4, 5, and 6. So I'm planning that to be on Monday, Tuesday, Wednesday. All right, so there's the agenda. You guys get on the agenda? Good. Great. Oh, also, second half of today, while you guys working on these, that worked out really well because I could just walk around and troubleshoot any questions. I had questions like how do you know like when you use bracket or parenthesis or like questions from multiple days, and yeah, so I was able to help out students individually. So yeah, same thing for you guys. So this is a good plan. Good plan. All right, so we're on lesson 1-3. So see that starts on page 25. So page 25. Okay. All right, so I got extreme and innovative behavior. Is there what? Huh? Yeah, got pencil sharpener. Okay. So extreme and end behavior. Okay. So same thing last couple days. So I'll read the intro with you guys, then solve some, and then give you guys solve the ones I find. Right. So if there's on a graph, if there's some maximum value or minimum value, those are collectively called extrema. Right. So a maximum is the highest point on the graph, the minimum is the lowest point on the graph. Now some graphs are not going to have a maximum or a minimum. They just continue forever in that direction. Like here, do you guys see this f of x right here? You guys, does this f of x have any maximum, or does it just go on forever? Yeah, it just goes up forever. Okay. But does it have a minimum?
Yeah.
Yeah. Here, what's that? The coordinate 0, -5. So you can say the coordinate 0, -5, or it has a minimum of -5. The coordinate 0, -5. Right. Now, there's another type of maximum minimums where they're called relative. So a relative max or a relative min is where there might be like a hill or a valley in the graph where, okay, it's not maybe the highest point or lowest point in an absolute sense, right? But maybe in this locality. So look at this g of x right here. Now, you can see g of x goes down forever, so there's no absolute minimum. Okay. Also, g of x goes up forever, so there's no absolute maximum either. Okay. You could go down negative infinity, go up to positive infinity. But I do see a hill here, and I do see a valley right here. So those are called relative extrema. So there would be a relative max at, ooh, guys, what's the coordinate of this relative max? Yeah, -2, 8. Yeah, so -2, the x value, and 8 is the y value. Or yeah, you say relative max of 8. Right? And then what's the relative minimum? What's the coordinate? 0, 4. Right, so 0, 4 is the bottom of the valley. Yeah.
I have a question, but I feel like there isn't a minimum and isn't a maximum because it keeps going up on like the two arrow points. It keeps going up.
Yeah, you're right. Okay, there's no absolute maximum, right? But there is a relative maximum. Yeah, a little bit different thing. Yeah, it's a good point of clarity there. Yeah. So yes, we got two different kinds. We got like an absolute maximum, we got a relative maximum, and the same thing for minimums. All right. Oh, and then okay. I like that your book always has real life type examples of this. Let's take a look. This can be fun. Okay. Social media posts as a function of time. So they start here at midnight, and then they go hours after midnight, where like the number of social media posts on some platforms. Right. Okay. So it looks like okay, midnight is pretty low, and then it peters out. 1 o'clock, 2 o'clock, 3 o'clock in the morning. It's like really low. Okay. All right, and then it skyrockets up. It looks like by it looks like guys, how do you interpret this? At what time is the absolute maximum number of social media posts?
Hour 11, no 12.
12 hours after midnight, which makes it
12 o'clock.
Yeah, 12 noon. Yeah, so 12 o'clock noon. 12 o'clock noon, there's an absolute maximum number of media posts, right? Then it dips a little bit to this valley. So does it 2 o'clock in the afternoon. So 14 hours after midnight, 2 o'clock in the afternoon. That's called a what again? What's the term for that?
Relative.
A relative minimum. Relative minimum. Right. Now, of course, not an absolute minimum. There's definitely other times of the day where it's lower than that, but in that locality. So it looks like it dips, right? But then it rises a little bit again to this hill. So it goes from this valley to this hill. And that'd be a relative maximum at was that 4 o'clock in the afternoon, 16 hours after midnight, right? Right. And how many are we talking about? Like, well, since I'm pointing to this point, this relative max, is it just over 10 units? Is that just over 10 units? Okay, so let's look carefully how it's scaled. Guys, this is how many posts. It's not 10 posts. It's 10 what? Yeah, hundreds of thousands. Hundreds of thousands. Okay? And if you have 1,000, is that like a million? Million, right? So it looks like this relative maximum here is just over a million. This relative minimum here is just over 9 million. And the absolute max was that like 11.5 million? Okay, so you guys see how to interpret that? That's yeah, okay. And then after 4 o'clock in the afternoon, it keeps going down to you guys see how this could cycle? Like it ends where it starts? And so you could have the next day, probably looks pretty similar to this one. So it probably cycles like that, right? I think. Okay. I've seen, well, there's similar curve shot for lots of phenomena. And I know like water usage, electricity usage have similar looking graphs. Right? And the utility companies, the water company, the electricity company, they know this ahead of time, so they can like scale down their production to match demand. Right? So those similar looking curves. Right? So the other main idea in your book is in behavior. So in behavior. Right? So what happens to a graph is it goes on forever to the right and forever to the left. Right? So let's do these two examples, and I think I'll make up some of my own. Right. So this first example, example A, guys, as you go to the left forever, does this graph just continue going up forever? Right. And the notation goes like this: it said you go as x approaches negative infinity, f of x or y, if you like, approaches positive infinity. Right. So x, you read this at this arrow as approaches. Okay. Especially when you get into calculus, there's a concept called limits. Like if you get close to something, you're 10 one way, but maybe you won't ever quite reach it. Okay. It's negative infinity. Like that goes on forever. Okay. So another way to say this whole bit as x approaches negative infinity is you go to the left forever. Yeah, kind of think of it that way on the graph. And then let's see f of x, or this could be your y value if you like, right? Like the vertical approaches infinity. Right, so this means you go up forever. Right? So negative infinity in the x direction plus going left, and positive infinity in the y direction plus going up. Okay. Right? You guys see how that could represent going to the left forever on this graph? Right? Yeah. Okay. Okay. Yeah. Okay. Okay. So as x approaches negative infinity, f of x approaches positive infinity. Go left forever, you go up forever. Okay, and then I could do the same thing for the right end because this is the left end behavior. Okay, that's what the graph is doing is you go forever to the left. But what about when you go forever to the right? So as x approaches, guys, what do you think goes right here? If you're going to the right forever. Uh, yeah. Okay, you guys good going left forever? Okay. All I'm doing is I'm looking at this line saying as you go left forever, you just keep going up forever. Up, to left. Okay. Now let's take the same graph, Okay. Let's go to the right forever. So how do I write that mathematically? I would say x approaches what?
Positive infinity.
There you go, positive infinity. Yeah, or just infinity if you like. Yeah. So now we're going to the right forever. To the right forever. Okay, so comma f of x, or your y value approaches. Okay. Now I'm looking at this graph right here. As you go to the right forever, what does your y value approach?
Negative.
Yeah, negative infinity. See how it goes down forever? Okay. Just feel like down forever. Okay. So a lot of graphs like will look like that. They'll tend, towards infinity or negative infinity, go up and go down forever. But not all graphs will. Some will approach horizontal asymptotes, so they'll be constant values. Okay, guys got this? All right, let's look at the very next example. Example B. We got a g of x. G of x. Okay. Guys, is this just a flat constant line? Okay. So for this example, maybe I'll okay, maybe I should draw the graphs too, right? Like if you're keeping notes and you're looking back at your notes, you definitely want to know what you're talking about, right? So x, y, and the graph basically goes like this. Okay. Left forever, up forever, right forever, down forever. Okay, that's one we just did. Okay. All right, now what about g of x? So g of x. Now this one got x-axis, y-axis. Looks like up here at 2 notches, we just got a flat line that just runs flat forever. That's g of x. The 2. Okay. So for this one, as x approaches negative infinity, so as you go to the left forever, you can say g of x, which is this pink line right here, approaches what? Guys, this pink line, is this pink line going up or down, or is it just staying flat at 2? It's just staying flat at 2. 2. That's it. 2. Okay. And as x approaches positive infinity, so now we're going forever to the right. Going right. G of x approaches what? Yeah, it's still 2. Yeah. Because it's just a flat line. It doesn't matter if you go 100 units to the right, if you go 1,000 units to the right, if you go 1,000,000,000,000 units to the right, the y value is still 2. It doesn't matter how far you go to the right, it's always 2. Right? Okay. Here's where I want to make up my own example. So something looks a little more exciting. Maybe I'll call this h of x. So y, x. Let's put on some horizontal asymptotes. Horizontal asymptote.
Horizontal asymptotes.
Horizontal asymptote.
What's that?
That's just like a flat dashed line. You guys get a flat dashed line? Suppose it came up with an equation that did something like this. I'd have to think about it. I'm sure I'd be able to come up with an equation that looks like this, but right. But let's say that's the graph. Right. I'll call this h of x. H of x, right there. Right. So maybe when x is 0, y is 0 on this graph, right? And then as x ticks along, tick, 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 tick. Okay. So the y value is always growing, but you see it kind of peters out. Right? Sometimes it's called like a logistics curve, if you ever see that term. Right? I know kind of a real life example where it looks like the right half of this graph. Have you guys ever seen, like, if you're working in a lab, suppose you have like some bacteria, you have like one of these little agar dishes. Have you guys seen those? Right? You take like a little Q-tip swab and there's some nutrition here, you go swab, swab, swab. Okay. And you come back after a few days and the bacteria is like growing or the fungus is growing or whatever you're growing in here. You guys have seen those?
Mm-hmm.
Like little agar dishes, like biologists, chemists, right? Doctors, right? Okay, now at the beginning, there's exponential growth. So like if it's bacteria or fungus, whatever it is, like it'll double, maybe every hour it doubles. But it can't do that forever because there's only so many nutrients in this dish. And then at some point it reaches like an asymptotic size. It reaches like some limit to how much can grow in it. Okay, so let's do the end behavior for this type graph. We can say as x approaches negative infinity, so we're going to the left forever. As we go to the left forever, h of x approaches what? Yeah, -2. -2. Yeah. Right. But like here maybe it's like -1.5, and here maybe it's like -1.9, and then -1.99, -1.999. But it's approaching -2, isn't it? Okay, yeah, it never reaches the -2. Yeah. So like if you let x go to like -1 trillion, maybe this could be a negative 1.999999, right? But it's sort of like approaching x. Right. And then what if you go forever to the right? So as x approaches positive infinity, h of x approaches what? 3. Yeah, 3. See how there's this asymptote up at 3? Is that? Right, guess that? See if there's anything else I need to cover here. No. Okay. I think that's all right. Okay. All right. Let's look at some of these. And I only assigned a few of them to you, and I have them highlighted here. So it looks like number 3 I assigned you guys. So I'll do number 1 with you guys. Number 1. It says, what were you doing? It says identify the x and y values of the extrema, okay, which are maximum and minimum. But let's also throw in relative max and relative min. Okay. So I'm looking at this number 1 graph right here. Okay. So looks like coming from the left, it's going up, and then it peaks and it goes down, and then rises back up again and goes up forever. So, guys, is there any absolute max or absolute min on this graph? No, there's that. Okay. So there's no absolute extrema. That's to say, maximum or minimum. But I do see a hill and a valley right here. I see a hill and a valley. So I could say there's a relative minimum at okay, so there's no absolute extrema, there's no maximum, there's no minimum. Okay. It goes down forever, it goes up forever. Okay. Okay. But there is a little hill and there is a little valley. So let's start with the valley looking one. Okay. Absolute, so the relative minimum. Okay. Like, I guess you can imagine if this was like a physical hill and you dropped a marble, it would shoot, fall into this little valley right here. Okay, what coordinate is that? Right there.
-1, -b.
Aha! Yeah, -1, comma, -3. So the x value is -1, and at that value, yeah, you're at -3. Yeah. And if you stepped a little to the left or a little to the right, either way, you have to walk uphill a little bit. That's that would make it a relative minimum. Okay. How about relative maximum at where do you guys think the relative maximum is? Aha! That's it. -2, comma, -2. So if you go from the origin to the left 2 and then down 2, yep, you're sitting right on top of a little hill. Yeah, relative maximum. Right there. All right. Can you guys find the maximum then? That down. Right. And here, just going to let's say number 3, number 4. Guys, do both of these have an absolute minimum?
Oh, yeah.
Yeah. I guess there's like some lowest point for both of them, right? Actually, it's a couple here and a couple here. Okay. So number 3 and number 4 do both have maximum. Absolute minimum, let's say. Okay. But they do go up forever, so there's no absolute maximum. All right. So skip ahead a little bit. Let's do number 10, roller coaster. Now this is an end behavior question. Guys, look at this graph. From the graph, you can usually figure out what's going on anyway. See, okay, so roller coaster height. We got height as a function of distance. Okay, and here in the setup, it says as a function of distance away from the starting point. So it looks like there's some starting point. It looks like immediately you go up this huge hill. Okay, and then as the roller coaster's going forward, huge drop, and then kind of a medium hill, and you drop, then kind of a short hill, and then you're now it kind of continues, it keeps going, sort of. Right? Maybe it kind of. Do you think it's gonna asymptotically approach ground level, and then loop back around to the beginning to get new passengers? Right? Right. And I think that's all it wants you to do is to it says describe and interpret the end behavior and the context of the situation. So the end behavior. So this is number 10. So in behavior, I could say the point 0, 0, which is the beginning, represents the beginning of the ride, which is at ground level. Like if somebody asked you to describe what's going on with that graph, which I just did for the last minute or so, right? That's pretty much one thing I would say. Right? Then I would say, right, how about going to the right? Okay, so as x approaches, I'll say infinity, although that's a crazy abstraction, but if I just kept going, right, could I say height approaches what? Okay, so this is a horizontal asymptote. That approaches what?
0.
0 meters. Yeah, yeah. 0 meters. Right. Which means that okay, so the coaster returns to ground level at the end of the ride. There you go. Right. That would make sense, right? Just gotta loop around and let those passengers off and get new passengers. Guys good? So you guys can interpret what these graphs mean. That's not too fancy, right? All right. Ooh, we got some model with a dolphin going on. That looks fun. Yeah. Yeah. By the way, this here, guys, if you ever see, guys, what shape is that right there? What shape is that? Parabola. Yeah. You guys see it's negative 16 t squared, blah, 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 something. Okay. Guys, this is whenever you are on Earth in Earth gravity, and you're talking about distances in terms of feet, right? Well, you'll always create parabolas that are start with like negative 16 t squared, something, something, something. And the rest of it tells you exactly how it shifted. Right? Now, in the metric system, you don't see 16s. You see like well, like half a tail would be 5 or something like that. Okay, just touch on that one. All right, let's do just a couple more. I just do a couple more. No, 3 more. I'm doing 3 more with you guys. Okay. So I assigned one of these down here. So I'll do a similar one. What does it want you to do? Identify the extrema. So how about number 15 I'll do with you guys. Let's do 15. I assigned 14, so I'll do 15 with you guys. 15 is this one down here. Guys, are there any absolute maximum on this, or does it just go up forever? It goes up forever. So I'll say no absolute maximum, or goes to infinity. Guys, is there a relative maximum?
Yep.
Yeah, got a relative maximum at, well, relative maximum. Is there basically one hilltop? Okay. And that's at the coordinate what? Yeah, it looks like 0, 3. Maybe this looks like it's slightly short of 3. No, it says round to the nearest 10th. Looks like a little bit short of 3, so I'll call it 0, maybe 2.9, something like that. Okay. Now, how about the minimum? Now, guys, those two minimums, now they are bottom of the valley, so I might almost say relative, but are they also absolute minimums?
Yeah.
Yeah, yeah. Okay, so I'll say they're minima at, okay, got 2 coordinates. Okay, so to both the lowest point. Take your, make your best estimate. What's this one right here about? Is it a kind of -4, but maybe a little to the left of that even? I'll say -4.2 maybe. And then how far down? Well, it goes -4 down, but then it goes down a little bit more. Maybe I'll say probably right about there. And at how about this one right here? This is like same thing mirrored on the positive side. Ooh, hey, do you guys think this graph has symmetry about the y-axis? Hey, did we talk about this yesterday? Guys, if it has symmetry about the y-axis, that's called what? Even or odd?
Even.
Even. Would this be an even function? I think it is. I think f of negative x is equal to f of x. I bet you could show that too. So at 4.2, negative 4.2. Okay. So you guys good on that one? All right. Oh, I did want to talk about number 18 bubbles because I saw, ooh, bubbles. It's got a graph. That sounds fun. I almost assigned this one, but then I saw there was a mistake in the setup in the premise. Okay. So here they have the volume of a bubble as a function of its radial size. Now, guys, is it true? The bigger radius of the bubble, the more volume it has. And at a glance, maybe the curve kind of curves up like that. That's true. Right. But guys, look really close at this text right here. There's a mistake, and I'm curious to see who can figure out what the mistake is in this premise. That's really what I'm going to do with this one. Is just see who can find what is the mistake in this one. Oh. Does anybody see it? No? Nobody sees it? Huh. Huh. All right. Good. Draw this out. Draw this out. So bubbles. So, ooh, could this be a bubble? Oh, shiny. You're gonna put a little circumference around it, sort of. Okay. Give it a radius. Let's give this radius r. So r could be radius, right? R is radius, right? Now, if I want to say, what's the volume of anything? Okay. How could I quantify that? Would it be square feet or cubic feet? Cubic feet, yeah, or square meters versus cubic meters. It's gonna be cubic meters. It has to be cubic something, doesn't it? For a volume, it has to be cubic something. So, guys, here's what I want you guys to know from high school. I want you guys to know things like this. Like the volume of something is proportional to its radius cubed. Okay? Okay? Okay. So does anybody know what is the exact volume of a sphere? I mean, a bubble is basically a sphere. You can use a sphere to model a bubble. What is the volume of the sphere based on its radius? Exactly. 4/3 pi r cubed. Right. So you guys see volume is proportional to r cubed. Right. All right. So that's what they messed up here. They said volume is 4 pi r squared. No. No, guys, something is 4 pi r squared, but it's not the volume. They picked the wrong formula. Guys, what's that? What do you say? What's equal to 4 pi r squared?
Bubbles.
Huh?
Bubble.
It's not the volume of the bubble, it's the what of the bubble.
The volume.
Guys, what's proportional to r squared? You can quantify in square feet. Area. Guys, it's the surface area. The surface, so V could be volume. The surface area of this bubble, which you can use in a sphere to model, that's 4 pi r squared. So the area of something is always proportional to r squared. This is square feet, square meters. Kind of think square inches could be. Okay, guys got it? All right. All right. So a little side quest there. All right, let's do one of these and then one on the next page, and you guys have the rest of the class. So it's use a graphic calculator to estimate the coordinates at which extrema occur for each function. Round to the nearest hundred. Right, so they're gonna spit out some really weird polynomials that might have like crazy extrema, like crazy decimals. Okay. Now I assigned number 25 to you guys. Now, if you have a graphic calculator, you can use that. If you don't, then you can do what I'm about to do, which is use. Ooh, guess what I'm about to use?
Desmo.
Desmos. Go to desmos.com, pull up the calculator. Okay, and you can just type in the function. I'm going to type in the function for number 24. Okay, I'm doing number 24. Number 24 says negative 2x to the power of 4. Then hit the arrow key. Right. Then it says plus, I'm just reading it straight out of the book. If you have your book, 5x to the power of 3. And arrow key. Then minus 4x to the power of 2. Arrow key. Then 3 times x. Then minus 7. Did that type right? Oh, hold on. Something looks off. No. That messed up somewhere. Let me go back. I did not type right. Get rid of this. Okay. It was 4x squared. Okay. All right. That's what I meant. Double check. Double check. Does that look like the book? Yeah. Okay. That looks like number 24 out of the book, doesn't it? Okay. And then Desmos will act as a graphic calculator for you guys. And oh, I'm hitting control and I'm just scrolling out. Okay, or I can just click and drag. Okay. That guys, that's what that function looks like. That's a crazy looking function, isn't it? Okay. Guys, oh yeah, what's that? Oh yeah, okay. Guys, does this have an absolute minimum or does it just go down forever? Yeah, it just goes down forever. But is there an absolute maximum on this? Yeah. How about
I don't have anything to say.
how about this point right here? This point right here. And if you hover over this point, it should give you a coordinate. Or it did last class. Oh, there it is. Okay, I have to click. Right. You guys see that right there? Right. That's probably pretty close to the maximum. So I would write that down. I would coordinate 1.34 comma negative 4.58. That'd be good enough. Okay, to the nearest 100. It said to the nearest 100, right? Right. So can you guys use Desmos and do that? Right. Or your own graphic calculator if you like. Right. Right. So let's do one more together. One more. Okay. So next page. I did assign these two to you guys, number 33, number 34. So I'll do with you guys number 32. It says sketch a graph of a linear function and a nonlinear function with these in behavior, right? So now you have to use some of your own creativity. Just like number 34, it's a very similar idea. Right? They specify some conditions, but there could be many, many correct answers to this, right? So number 32 says as x approaches negative infinity, so as you're going forever to the left, f of x approaches infinity, so that means you're going up forever. Also, as x approaches positive infinity, so if you're going to the right forever, f of x approaches negative infinity, so you're going down forever. Okay, so left, here you just keep going up. And to go to the right, you always keep going down. Okay. And it wants one linear and one nonlinear. Hey. Let me pause this. All right, we're back here. Right, so what's a linear function that goes up forever as you go left forever, and then what's a nonlinear? Right, so 32. Okay, I'll do one of each of you guys. Let's do one linear and one nonlinear. So x, y, x, y. Okay. Yeah, there could be many, many, many correct answers to these. So I'll just count some simple. Okay. What if I do this right here? Okay. Could that go up forever as you go to the left forever, and go down forever as you go to the right forever? So that could satisfy. That would be a linear equation. Yes, could this possibly be y equals? How could this finish out? Yeah, negative x, and it looks like I have an intercept here. It's like plus one or whatever. Right, whatever. That could figure out, right? What about this? What if I have y equals negative x cubed? Right. That's the next one I'm going to make. I'm curious to know. Okay, so if I just spit this function at you, y equals negative x cubed, I wonder how many of you guys could whip off a basic shape of that graph. How many of you guys know what that graph looks like? Okay, yeah, looks like, okay. Here, show of hands. How many of you guys know what this function looks like? Okay, yeah, a few guys. Okay. So yeah, let's go ahead and plot this. Pause. Now, if you never know what a function looks like, can you just very simply make a table of x, y values, x, y, and just plug in some random values and see what happens? Right. So let's try where x is negative 2, negative 1, 0, 1, and 2. Those could be good values, right? Just we probably figure it out from there. How about 0? If I plug in 0 for x, what does y have to equal? 0. Right? So 0 cubed, make it negative, it's still 0, right? What if I plug in 1? Guys, what's 1 times 1 times 1? 1, and then a negative 1? What if I plug in 2? Guys, what's 2 times 2 times 2? 8, and then make it negative. So negative 8. Ooh, it's taking off real fast. Let's go the other way. What if I plug in negative 1? What's negative 1 times negative 1 times negative 1? That is negative 1. Okay. But then I also have to include this negative. So now that's like 4 negatives, right? So overall it becomes what? Yeah, positive 1. Okay. What if I plug in negative 2? What should this come out to? Yeah, positive 8. Okay. Because negative q cubed is negative 8, and then there's also this negative makes it back positive. Okay. So let's plot those points. So I got 0, 0. I got 1, negative 1. I got 2, negative 8. So negative 8 like down here basically. I got negative 1, positive 1. And negative 2, positive 8. Just like up here. Okay. And I think again, some of you guys do this from the beginning, do this from the outset. Okay. Or maybe some of you guys remember that now. Does that look sort of familiar? Negative x cubed? Like, oh, okay, let's do that. Okay. And does this match the same end conditions? If left forever goes up forever, and right forever goes down forever. Yeah. So that could do it. That could satisfy that. All right. So you guys have the rest of the class to work on your puzzles and ask me any questions. So I will be in the vicinity if you need me. Call me over. I can help you with any questions you have.